それではただいまより2007年第23回日本国際賞の受賞者によります受賞記念講演会を開催いたします。講演に先立ちまして、財団法人国際科学技術財団理事長の吉川より主催者を代表して一言ご挨拶を申し上げます。理事長、お願いいたします。
吉川です。日本国際賞は科学技術において、独創的、飛躍的な成果を上げ、科学技術の進歩に大きく寄与し、かつ人類の平和と繁栄に著しく貢献したと認められる人、そういう科学者に贈られるという賞でございます。で、毎年2つの分野で受賞がございまして、最初、第1回の受賞というのは1985年でございましたので、今年は第23回になります。本年の授賞式はちょうど明日、4月19日に国立劇場で行うことになっております。それで今年のその、受賞、日本国際賞では、毎年基礎研究の分野、およびそれが社会にどういうふうに貢献したかという観点で、いろいろなテーマというのを選んでいるんですが、今年のテーマは2つございまして、1つは基礎研究が発信する革新的なデバイスということです。で、もう1つは共生の科学と技術と、こういう2テーマになるんですけれども、基礎研究が発信する革新的デバイスの方は、お二方の共同受賞になっておりまして、アルベル・フェール博士とペーター・グリュンベルグ博士であります。で、アルベル・フェール博士はフランスのパリ南大学でずっと研究をされていたんですけれども、今日お話がありますのは、その業績である巨大磁気抵抗を、これを発見されたわけですが、それが発見だけではなくて、その後さらにスピントロニクスという新しい学問分野を開くという大変大きな衝撃をこの分野に与えた。同時にもご存知と思いますけれども、巨大磁気抵抗というのはすでにもう応用されておりまして、この計算通信の分野で非常に重要な技術となっているというわけであります。で、同じくペーター・グリンベルグ博士、これも同時にこの巨大磁気抵抗を発見されたという大変珍しいケースなんでございますけれども、その後も相互に連絡を取りながらこの分野を共同で支えてきたという方、この方はユーリッヒ固体物理研究所というところにずっとおられまして、現在もそこで研究を続けておられているというわけです。で、もう一つは全く違う分野で共生の科学と技術ということで、この分野は英国のピーター・アシュトン博士が受賞されました。で、アシュトン博士は熱帯林ですね、熱帯林の中で、暮らすことをですねが最初の経験で、お若い時にそういうところで暮らすということで、フィールドでずっと研究をされるという、そういう熱帯林の研究を始めまして、生物多様性について大変大きな貢献をされたわけですけれども、ご存知のように最近はこの生物多様性というのは環境問題の中で最大の課題の一つになったわけで、このアシュトン先生のご研究というものが非常に大きないろいろなものを考える上での基礎になっているという状況が現代を特徴づけているのかと思います。で、これから3博士の受賞記念講演を行っていただくわけですけれども、お三人もぜひこの皆さんとこういう自分の研究というものを通じていろいろ対話したいと、こういうことでこういう一般講演ということを企画させていただいたわけですけれども、ぜひ皆様もこの受賞されたお三方の科学およびその社会への貢献というお話を通じて、これからの科学の発展ということを考える上でさまざまな示唆をやることを期待いたしまして、私の最初のご紹介、ご挨拶といたします。ありがとうございました。
それでは早速講演に移ります。途中で休憩がありますが、前半は最初の分野であります基礎研究が発信する革新的デバイスという分野で受賞されましたお二人に講演をいただきます。フェール博士にはスピントロニクス、その始まりから未来までというテーマで、グルンベルク博士には次世体積層構造におけるスピン輸送現象というテーマでご講演をいただきます。 最初にですね、グルンベルク博士にご講演をいただきます。
So, good afternoon, ladies and gentlemen. Welcome to my talk, and also very much welcome to all my old friends who are most of them sitting here also. Thank you for this opportunity. So the title of my talk then, Spin Transfer Effects in Layered Magnetic Structures. I will first give an introduction, then come to a personal review, how it all started for me, how I got into this field. Talk about that also a little. Then we'll come to interlayer exchange coupling and tunnel magnetoresistance across insulators and semiconductors. After that, we'll turn to the metallic layered structures, metallic interlayers in particular. And there we'll talk about coupling and giant magnetoresistance. And after that, briefly, only the most current topic now, the latest topics among these, current-induced magnetic switching, SIMS, and Albert will also extend that to current-induced magnetic excitations. And I also hope that I have enough time to name some applications and show what's going on in applications of all this physics which is presented here. Okay. I have to, yeah, here we are. Okay, so let's get started with the introduction. And here I summarized a little bit what is most important to understand electrical transport, I mean currents and voltages in bulk ferromagnets first, then we'll come to the layered structures later. And one of the most important facts is the discovery by Stern-Gerlach. Already it was supposed before, but Stern-Gerlach verified it in the experiment, namely the spatial quantization. They did that on a beam of silver atoms, which I do not go into here, but I just have drawn what it means for electron spins in a ferromagnetic metal. There, this spatial quantization means that the electron spins can only be parallel or anti-parallel to the magnetization. We call that spin up and spin down. And the fascinating fact is that quantum mechanics does not allow any other orientation. So quantum mechanics leads to quite a strong simplification as far as the orientation of the spins in ferromagnetic metals is concerned. Okay, now when we go into electron transport, now we have also to understand that the electrons are not only aligned parallel or anti-parallel, but when we apply a voltage, suppose the voltage is from bottom to top, and then the electrons start to drift in the direction of the applied voltage, and they are very often scattered. Most of these scattering processes are without turning the spin around. These spin directions are very stable, but some of them, sometimes also a spin flip occurs, but for the following, we will neglect mainly the spin flip scattering, only this normal scattering we will consider, and that leads to the electrical resistivity. So in MOTS 2 current model then, when the mean free path for diffusion is much shorter than the mean free path for spin flip scattering, then the total current can be described by two currents in parallel, one with spin up and one with spin down, which sort of flow parallel in this body. And the equivalent circuit for the electronics people is like this, very simple. Two resistors in parallel, each representing the scattering rate of the associated electrons. Okay, so these are the basic features of electrons and currents in solids. And now we come to layered structures for reasons which become, I hope, apparent during the talk. Namely, these layered structures we consider the most simple structure where we have two ferromagnetic films, here indicated by the magnetizations. These black arrows are supposed to be the magnetizations, which can be oriented with respect to each other, either anti-parallel or some other angle, or also parallel. We consider as ferromagnetic metals for these layers transition metals like iron, cobalt, or nickel, or alloys of this. And then we have interlayers by which they are separated. And we consider the interlayer materials as non-ferromagnetic metals like silver or chromium. Or we can also choose semiconductors like silicon or insulators like magnesium oxide here. And the thicknesses of these interlayers are on the order of 1 nanometer, 10 angstroms or a little more. And the ferromagnetic layers have thicknesses on the order of 10 nanometers or 100 angstroms. Okay, so these are the systems which we consider for the following. All right, here we are. Now, the first experiment using such structures and also looking into electron transport was the one by Julier already in 1975. But he received only about 8% magnetoresistance effect. I will define that a little later, what magnetoresistance effect is. Only about 8%, and this at low temperatures. So that seemed not to be too interesting for the applications, for example. And that was also in a way forgotten or not well known until a rediscovery took place in 1995, when this effect was also observed at room temperature and also with higher values. And that was done by Miyazaki in Sendai and Modera in the United States. So I'm using this consideration of Julier here now to demonstrate the spin dependence of a transport process, which is here the tunneling process of electrons from one ferromagnetic film to the other across the insulating interlayers. That was the experiment. And Julier did that for the parallel orientation of the magnetization and measured a certain resistance for the tunneling current here. And then he compared this result with another where he had the anti-parallel alignment of the magnetization, did the same experiment, measured the resistance for the tunneling current, and found that the resistance in this orientation is larger than in the other one here. And he explained that effect now in the following way. He says, what we have here is a spin-dependent tunneling effect. The tunneling process here depends on the orientation of the spins, as we have seen before in the previous slide. And that generates a higher resistance here. One can discuss that in a little more detail as it is shown here. That is a little bit more for the physicists and the experts. We describe the ferromagnetism mostly by a band structure, which is shown here. I discuss here only 3D bands to make the effect more clear. But what happens here when we have a transition of the electrons going from here to here in the band structure scheme, we have the tunneling process indicated by here the green and the red arrow, and that is separated for the spin up and the spin down. And Julier claimed that this effect has to take place with the conservation of the spin here, so from this band to this band. And now one can see immediately that this has a different transition probability, because the strength of the effect depends on the product of the initial states times the final states into which we tunnel. And therefore, this process is dependent on the spin direction. It is, for example, here stronger for the red arrow because we have a larger density of states on both sides, therefore this is stronger. And with this assumption, then one can analyze the effect, and there is some mathematics written down here. One can now formulate with these density of states at the Fermi level, one can define a spin polarization as is given here, and express the tunnel magnetoresistance as the difference between the resistances for these two states normalized to the resistance in the parallel alignment. Okay, so with this, Julier then made the first attempt to interpret this phenomenon, but obviously what is missing here is any property coming from the interlayer, because we have the density of states only of the ferromagnetic species here, and no property of the interlayer is involved here. So we probably can say that this cannot be quite right. Must have been some influence also of the interlayer material, and that we can correct by simply replacing the spin polarization as is defined here by the density of states of the ferromagnetic metals by another one which we call the effective spin polarization, and describes the whole tunneling magnetoresistance effect in terms of this effective spin polarization, which includes also the properties of the interlayer, for example, reflection of electrons and so on, and describe it then in this way. And this effective spin polarization will be one of the most important quantities then also for the following. Okay, now that was the spin-dependent tunneling. Now, there are in these layered structures, there are more processes which are spin-dependent. Again, I have to remind you that we have the spin-up and spin-down electrons here in the ferromagnetic metals due to the spatial quantization. And now there are other processes for the electron transfer from one ferromagnetic film to the other across the interlayer. When here we have, for example, metallic interlayers, then we can have multiple reflections of the electrons while they pass from one layer to the other one here. And it turns out, and I will indicate it also later, that this spin-dependent transmission here and the multiple reflection is responsible for interlayer exchange coupling. Then we can have, during this process of the transmission, we can have also scattering of electrons. And this scattering can also be different for the spin-up and spin-down electrons, so spin-dependent scattering, in particular at interfaces here. And it turns out that this is responsible for the giant magnetoresistance effect for currents flowing in the plane of the sample, but also for currents flowing perpendicular to the plane. When the current is perpendicular to the plane, we have, in addition, interface reflectivity, which is also of influence here. Then this one we discussed, in fact, already, spin-dependent tunneling and reflectivity at insulating barriers. It's responsible for coupling and tunnel magnetoresistance in these structures. And finally, the most recent topic, which is very active now, is spin-dependent reflectivity, leads to current-induced magnetic excitations and switching of the magnetization. So here we have a strong current flowing perpendicular to the sample plane, and due to the current, the magnetizations can switch. I will go in a little bit more detail later. Okay, so now I promised you to tell you a little bit how it started for us, how we got into this whole field. And then I start with our institute in Jülich in 1975. I think some of you still know Professor Zinn. He deceased meanwhile, unfortunately. And I was working with Fatma Metavi here and Manfred Helden, who were students of Professor Zinn, and I had to supervise them myself. I'm hidden in here somewhere with two beards still. And we decided at that time, I came from Canada and did light scattering before, so I was very excited about light scattering, and I was also very excited about an instrumental development which took place at that time, promoted by John Zenderkog in Zurich, the multipass Fabry-Perot interferometer, which is, for example, good to measure light scattering with very small frequency shifts. And since we were in the Magnetism Institute and europium oxide was one of our favorite materials, we decided that we want to see spin waves, which was always a dream of mine as a student to look at spin waves. And we decided that we look at spin waves in europium oxide with this kind of instrument, which we built up there also in Jülich. And indeed, after a short time, we were able to get spectra, and the spectrum is shown here. And there were two peaks, M1. This is, in fact, one peak, M1, I call it, but Stokes and anti-Stokes scattering here. Maybe I should not go into too much details of the light scattering process. So one can observe always Stokes and anti-Stokes observations for these spin waves. But then there was an additional peak called here M2, of which we didn't know what it comes from. And for some time, we were always wondering what that is, that additional peak M2. And then we were lucky because our cryostat broke down and had to go to the workshop. After it came back from the workshop, we reassembled everything and found and repeated the experiment. And now you can see this additional peak M2 is on the other side. So after some thinking then also in literature search, we found out that what we had seen was the famous Damon-Eschbach surface mode of the europium oxide, which propagates on one side of the sample only in one direction, not the opposite. And that depends on the sense of the magnetic field. And what had happened after this repair was that the leads of the magnet were interchanged to the power, connecting to the power supply. And for that reason, the magnetic field was pointing down, and this additional wave was propagating in the opposite direction, and then was observed as an anti-Stokes light scattering phenomenon here. So finally, this repair helped us in order to identify such a spectrum here and find out that it was the Damon-Eschbach surface mode with its unidirectional propagation along the surface. Okay, so we were very excited, of course, about this discovery and stayed with the study for quite some time and extended that to layered structures. And one of the most important results turned out to be this one. When we have a layered structure, when we looked into double layers, for example, iron, chromium, iron, and one manages to get an anti-parallel orientation of the magnetizations, here indicated by the blue arrows here, then one can predict that for the Stokes and anti-Stokes frequencies, which one observes from these coupled Damon-Eschbach modes now, one expects here the frequencies are plotted for the Stokes scattering and for the anti-Stokes scattering here, that they are different. So we're very excited about that and tried to see that in various structures. And finally, we were indeed successful. In 1986, found that we had this kind of spectrum, which meant that the magnetizations of the iron-chromium iron system, which we had investigated in that experiment, was indeed anti-parallel, and then that was the discovery of anti-ferromagnetic type coupling of iron across the chromium. So simply following these features of the Damon-Eschbach mode and the coupled modes finally led to the discovery of this anti-ferromagnetic interlayer exchange coupling of iron across chromium. Okay, now when we published that, we realized that there were others also in the field who did very nice experiments with neutron scattering. And at the same time, when we published in 1986, there were two other works on dysprosium, yttrium, dysprosium layered structures and gadolinium structures, where they, by means of neutron scattering, also found this type of coupling. They are not leading always to anti-parallel alignment, but to helical structures, but the physical origin, interlayer exchange, was the same. Okay, maybe just brief this. Later on, many people, and ourselves too, measured the coupling with simply by remagnetization curves, which gives a very strong shearing due to the coupling, to the anti-ferromagnetic type coupling. But one can say that shearing of hysteresis curve is a very general phenomenon. One observes that very often, so this is very unique. So it was not a luxury to first apply this more sophisticated light scattering experiment, which is indicated here by the spectra also. And here this is, excuse me, this is compared to a non-coupled sample where we have the ordinary hysteresis curve with a small corrosive force. Okay, so now let's jump into more modern times. You see already here that was work from 2003. Matthias Buchmeier in Jülich finished his PhD thesis, and I take some work from his thesis here. Let's again go into the light scattering spectra, and we start with this layered structure here. We start with a very small silicon thickness of only 0.5 angstroms here for the lowest spectrum, and you can see that this is quite symmetric to the elastic line. So no such asymmetry as I showed before. And now you should not be too much concerned about the different intensities here. This is an artifact of the magneto-optic interaction by which the light interacts with the magnetization in the light scattering experiment. But the frequencies are symmetric to the elastic line. And this is typical then for the ferromagnetic coupling and the parallel alignment of the magnetization. When we increase the silicon thickness, finally you arrive here at 7 angstroms of silicon, and you see a very strong asymmetry again, as you saw for the iron-chromium iron system before, and that indicates the anti-ferromagnetic alignment and the anti-ferromagnetic type of coupling. Now, it turned out that we worked on this system, in fact, for a couple of years and improved all the time, we think, the growth. And the coupling also became stronger and stronger until finally we got this result with about 6 millijoules per square meter. This is a measure for the coupling. It's in fact the coupling areal energy density. And this value of 6 is, as far as we know, the strongest coupling, antiferromagnetic type coupling, which has been observed up to now reliably. There are sometimes you find bigger numbers in the literature, but they are, I think, not so reliable, but we can guarantee, so to say, for 6 millijoules per square meter. The next strongest coupling is the one found by Stuart Parking with 5 millijoules per square meter for ruthenium interlayers. This is also a very strong coupling, and it is also considered for applications, as I will show later. Now, this type of coupling, as is indicated in here, is so strong that when we apply to samples which show the antiferromagnetic coupling and have antiparallel across the interlayer, these are the magnetic layers here, there is the interlayer here, and on both sides the magnetizations of the ferromagnetic layers wants to be anti-aligned, but the external field does not allow that, twist them a bit. But this coupling is so strong that we have here not the full alignment, but we have a twist to a larger angle here across the thickness of the iron film. So this twisted state, which is reminiscent of the Bloch wall, demonstrates this strength of the coupling, which is here in competition with the external field. Okay, now I would like now to come back to this effective spin polarization and give you a very simple model for the coupling across insulating materials, a very simple consideration how we can imagine how that comes about, how it works, that we have this type of antiferromagnetic coupling, or also ferromagnetic. Here it's ferromagnetic assumed. And in order to see this, one has to consider that electrons at the Fermi level in such structures here, even though we have an insulating interlayer and we have the tunneling process, all the time cross the interlayer and so to fly back and forth across the interlayer. That is due to the high energy at the Fermi level, which brings them always to change the film across the interlayer and go back and forth. And when they do that, they, so to say, maintain again their spin polarization, which I told you in the beginning is rather stable, and carry their spin polarization from one film to the other. So all the time, spin polarization is carried from one film to the other across the interlayer. And due to this, we get an alignment, and this is obviously parallel when the spin polarization is positive, meaning that the electrons which change the layer are parallel to the magnetization, then they would order this film also parallel to the first one. But when this one is anti-parallel, when we have a negative effective spin polarization for these electrons, then the electrons which start here and go over and have the negative spin polarization, the majority of them would like to align this anti-parallel, so finally that will align anti-parallel. And when we start now from here, we have to take again the negative spin polarization, that is now the spin pointing up here, comes over to the other side and wants to rotate this one into the parallel, which is already here, anti-parallel to this. So that is the mechanism then of antiferromagnetic coupling due to the effective spin polarization, which is carried over from one film to the other. Okay, so this is very simple, and we thought for some time maybe this is an oversimplification. That is not really true. That is too simple. But so we did some calculations using formula from the literature, and I do not go into the details. That was the free electron model here for the experts, and the formula developed by Johnson-Sefsky. And here we see now the spin polarization, again, as a function in this calculation, as a function of the barrier height here. And we see that it crosses at some barrier height, it becomes negative, goes from positive to negative. And then when one calculates with the same formula, also the effective interlayer exchange coupling with the black curve here, you see that it also changes sign at that point. So it supports this idea, this simple idea, that it is due to the effective spin polarization for the electrons which cross the barrier. And then we can calculate also the tunnel magnetoresistance effect that only has a minimum where we have the negative, where we have the minimum in the spin polarization, or the zero of the spin polarization, the minimum, but that the spin polarization enters squared into the expression for the tunnel magnetoresistance. Therefore, this is also expected that it increases again then, although we have the negative spin polarization, but it does not, the sign doesn't matter here for the tunnel magnetoresistance effect. And that seems to have been also observed by Miyazaki et al. In Sendai, which is the plot here. Again, the tunnel magnetoresistance expression as a function of the barrier height is given here, and we see for small barrier heights, again, this kind of increase. There's not too much work in the literature on this point, so this, in fact, one of you are found. There's other work also here from Japan, where this simply decreases. The upswing is not observed anymore, but at least this going down of the tunnel magnetoresistance effect with the barrier height is also observed in this work. Okay, now this is the most recent and very exciting topic concerning tunnel magnetoresistance. I have to refer to Albert Ferti, who will go in more details in this, but I cannot leave that out. Talking about tunnel magnetoresistance, one has to show this result here, this beautiful result after theoretical prediction by Butler et al. And Maton et al. In 2001. It was realized Vyasa and Scuba and Parkin and Almaden, this very strong tunnel magnetoresistance effect. Meanwhile, that was still around 200%. Meanwhile, the value has climbed to about 500% tunnel magnetoresistance effect for that particular system. It's a very exciting topic. Okay, now a few words about oscillatory interlayer coupling. I do not spend too much time on that because one of the more important aspects we have seen already, this is the exchange of spin polarization of electrons across the barrier. Now, for the electrons, it's even easier. Now we have metallic interlayers, and therefore, as I announced already in the beginning, we have multiple interference effect for these electrons. And that is reminiscent of a Fabry-Perot interferometer, by which, in fact, we discovered this in a way by this instrument of Fabry-Perot. I mentioned it in the beginning. In the Fabry-Perot, when you have monochromatic light, the transmitted light oscillates in its intensity as a function of the distance between the two mirrors. So this is an optical instrument. And in a similar way, here we have multiple interference effects in these layered structures, and now the interlayer exchange coupling oscillates as a function of the interlayer thickness. But the reason is, like here, a multiple interference effect now for the electron waves, which gives rise to these oscillations. And there are various experimental examples. I just show here one, which we did in Jülich from the iron-chromium-iron system, which we did not see yet in the beginning, but later on we found these many oscillations, and which supports that from the experimental side. And then there is that very famous, which I also have to show, this very famous experiment from the NIST group in the United States where they saw this oscillatory coupling for the iron-chromium-iron system by means of magnetic domains. I do not go into the details of that, but these many stripes illustrate this oscillatory coupling for this particular system. And the samples here were so perfect that even the famous spin density wave of chromium, which appears only for chromium, which is extremely perfect, was already seen also in these oscillations here. But as I said, I do not want to go into the details of that. Okay, so let's now come to the giant magnetoresistance effect, and allow me a short look at the watch. Yes, I should not lose too much time. So giant magnetoresistance effect, the dependence of the resistance on the relative magnetization orientation in all metal structures. Here's the configuration. Now we look at first only into currents in the plane of the sample indicated here. This is our double layer again. And then on both sides we put contacts and measure the resistance for a current which flows in the sample plane, illustrated again here with the magnetization orientation, and here anti-parallel. Here the resistance is higher, And record values at room temperature which have been found for these systems are on the order of 20% for the cobalt-copper-cobalt system. And this is a tri-layer, but in multi-layers, and Albert will also show results. No, I myself will show results in a moment, sorry, of about 80%. These are record values for this effect. Okay, so these are the first experiments. The FAT group in Orsay and ourselves here. This was done on a multi-layer, and the values which we got, as I said just before, was on the order of 80%. In our case, it was only 1.5%. That was only for the double layer, only 2. That was for the multi-layer. So there is a considerable enhancement of the effect when one goes to a multi-layer. Okay, what is the explanation? Now I make it again very simple and make very, very strict assumptions here to simplify the problem, but I hope I hit still the essence of the phenomenon, although I have these assumptions which make it very simple. Here again, the current flowing in the sample plane here, the magnetizations, here parallel, here anti-parallel. And now we assume that in the extreme case, one sort of spins is not scattered at all. These are the pointing ones which are pointing up here, and the others are scattered. And we assume as a representative for the whole electron motion, which is this back and forth, as I showed in the first slide, we look only at one passage of an electron going from here to here and being scattered, because it is a down electron, being scattered at the interfaces. And the other electron is not scattered at all. That would mean that in this extreme case, it would generate a short circuit, and the resistance would be 0. This is in the equivalent circuit is demonstrated here in this branch, which corresponds to the spin-up electrons here. There is no resistance, then we would have 0 resistance here. Okay, when we turn one magnetization around, this electron, which was not scattered at all here, is now scattered here because, according to our assumption, it's now a spin-down electron. It's opposite to the magnetization when it comes to here. His magnetization is here down, and therefore is now also scattered. So we have an increase from 0 to some finite value that would be infinity, in fact, for the giant Magneto resistance effect. But in reality, of course, they are all scattered to some extent, but it is sufficient that one type is scattered more than the other. And that generates, for this magnetization alignment, generates a larger resistivity than here, and this is the giant Magneto resistance effect, and its relation to the orientation of the spins, to the spin-dependent scattering, as that was already suggested in the first work by the Orsay group, by Fert and al. For this experiment. Okay, now, okay, I think I cannot leave that one out here. Later on, so these were all still samples which were anti-ferromagnetically coupled, and the anti-parallel alignment was achieved by interlayer exchange coupling. Later on, a short time after that, was found that the interlayer exchange coupling is not so essential. If we achieve an anti-parallel alignment of the magnetization by some other means, hysteresis effects, one hard layer, one soft layer in an external field, the soft layer remagnetizes first, and then we can also get an anti-parallel alignment. That was done here. The giant Magneto resistance effect also occurs. So the coupling is not so essential, but the anti-alignment and the different alignment of the magnetizations on the two films, that is essential, that we have to have in order to get this giant Magneto resistance effect. Okay, I'm always hitting the wrong button. Okay, now let's come to the current-induced magnetization switching and excitation of spin waves. I will only briefly mention the switching of the magnetization because the interpretation fits very nicely into the spin polarization consideration, which I did for the coupling before. So I would like to present that also here, although Albert Fert will go in more details of that and show you more results and also about the excitation of spin waves. I will not talk about that at all. So what do we observe here? The first experiment, by the way, were done by Katin, 2000 already. what do we observe? So let's assume we prepare a layered sample of that kind. Again, we see here cross sections before us with the fixed magnetization, so the so-called hard magnetic layer where the magnetization stays fixed, does not react to an external field, at least not very strongly, and for a small enough field, not at all. And the other layer is free to rotate, and then we drive a very strong current horizontally here. And suppose in the beginning the free layer is aligned anti-parallel to this one, then the current, and I can demonstrate that by the simulation. No, sorry. How should I do that now? I don't see any way to. No. Okay, then I have to tell that what should have happened now. So suppose we start with an anti-parallel alignment here, it drives the current here horizontally, then it turns out that this magnetization turns around and is parallel to this. And when the current flows in the opposite direction and we start with the parallel alignment, then the reaction of the system to this current is that this finally rotates into the anti-parallel line. It's a pity that I cannot demonstrate that here with the. No, it does not obey what I want to do. Okay, then let's go on to the explanation of the effect, which is very similar to the one I use for the coupling. So let's look at this arrangement first. We have the fixed layer, we have the free layer, we have the interlayer here, and now let's assume that the spin polarization of the electrons, as is illustrated here, we have more spin-up electrons than spin-down electrons. They carry their information over to here, and obviously this leads to anti-parallel alignment. When we go back, then the electrons would also then, okay, now I have to assume, because this is now different from the previous case, now I have a strong current flowing in this direction. So I can consider for the current, I can neglect the other electrons which go opposite. But due to this strong current, some electrons will also be reflected at that interface and come back. And let's assume that this reflectivity is stronger for the electrons with the anti-parallel alignment. They would like to rotate this magnetization as they come back into the opposite magnetization direction, but that doesn't happen because it is the fixed layer, so it does not react. Okay, so with this orientation of the current, then we would have the parallel alignment as predicted. For the other case, when the electron flux is in the opposite direction, we start again with a positive spin polarization here, and that would align this one parallel, but that is already parallel, so nothing happens. But now we again assume that we have a stronger reflectivity for the spin-down electrons, and when they are reflected back and come back into this layer, they would align this one now anti-parallel, and this is what happens. So that switches into the anti-parallel orientation. Now we have only to ask ourselves, did the situation now change completely, and we have to make a new consideration which will turn that again into the parallel alignment. Therefore, I make this in addition here to show that it is now stable, because when we have now the current flowing this direction as before, then again we have this this polarization for the spin-down electrons. They would like to turn that around, but nothing happens because this is a fixed layer. Instead, spin-down electrons are reflected back into the free layer and stabilize this orientation of the magnetization for that case. So that is indeed then the right result to explain this coupling, this switching of the magnetizations due to this strong current. Okay. Here I would like to show you a recent example how that can be observed now experimentally. What is plotted here is the giant Magneto resistance effect of these samples for a current flowing perpendicular to the sample plane now. And we see different steps here. This is as a function of the applied current, which is in one direction for the negative here, and this for the positive. That would be this the current flowing from the right to the left here, that is here positive, and we see the many steps here which indicate the switching of the magnetization due to this current. Okay, and more of this you will hear in the talk of Albert Pferd. Okay, so I think with these effects I'm rather through, but I would like still also to present some applications. Let me just have a look how much time I have for this. Okay, so now the giant magnetoresistance effect has had a lot of applications in magnetic field sensors, and essentially there are two types of sensors now on the market. One with exchange coupling, as is indicated here. So this is a multi-layer, like in that first experiment by Pferd et al. You use also the multi-layers and get a very strong effect. And one can use now also the antiferromagnetic type coupling in order to have a defined orientation of the magnetization without external field. This is why this coupling curve is shown here with negative and positive parts corresponding to ferromagnetic and antiferromagnetic coupling. Here the ferromagnetic coupling is on the positive side. Okay. So with this one can use a multi-layer for a magnetic field sensor, where then the magnetization starts to count when we apply an external field. And by using different values along this different thicknesses of the interlayers and different values for the coupling constant here, one can tune the sensitivity of such sensors here. And yeah, this is one advantage. But there's also a disadvantage, and that is that in the zero position, we have the anti-alignment. If the external field is zero, we have the anti-alignment. And then for positive and negative fields, we get a decrease. So the sensor in this construction works only for one direction of the magnetic field. It's unipolar. It gives the same signal for positive and negative fields. That's what I wanted to say here. Okay, but the advantage is that we can use multi-layers and get to quite a high sensitivity. There's some values here, 44% for this type of sensor in the maximum here. Okay, applications for this. Gear wheel, tooth detection. There is a magnet to assist this and magnetize the teeth of a gear wheel here, and the sensor which is close here to the gear wheel senses the magnetization. Therefore, they can be monitored. The other applications is cars, wireless steering here, using this as a rotational sensor for the steering wheel shaft here. Okay, then in vehicle detection, many vehicles have enough ferromagnetic parts in order to be able to detect it, to be detected by such magnetic field sensors. This is for streetcars here or for other cars. On airports, one can monitor airplanes also with this for safety reasons. It has some advantages compared to radar, because radar you sometimes cannot receive when the airplane is behind some building or somewhere. Then putting magnetic field sensors here would help also. There are field tests already for this application. And this is the one I like most, because I often have problems when I enter a park house to find a slot. And then in future park houses, one probably will have magnetic field sensors for each slot here. That is then the park house and with the slots and the field sensors. And then at the entrance, this information then can be given to the entrance on a panel, and you can decide where to go, because you find already then where you find an open slot when you continue to go into the park house. So I like that most, I must say. Okay, now let's come to the other type of sensor, so-called spin valve sensor. The one we showed before was the coupled one. This is the uncoupled sensor that consists of a free magnetic film and a fixed magnetic film. And the fixed can be conventional way, simply by using a natural antiferromagnet close to the fixed layer. Then there are also synthetic antiferromagnets exploiting antiferromagnetic type coupling. So this one then is fixed. That has the advantage that it is bipolar. this type of sensor reacts to positive and negative field and distinguishes also positive and negative field. But the sensitivity is not so large because one can only effectively use only one unit. That doesn't work in a multilayer because then that would be interrupted here by the so-called antificial antiferromagnet. Okay, but nevertheless, this has led to the most important application in this whole field of giant magnetoresistance, namely magnetic recording. And there is such a spin valve type sensor shown where the spin valve, where the fixed layer, this is obtained by other means, for example, by having permanent magnets adjacent to the fixed layer here. It holds the magnetization in one direction, whereas the other magnetization can rotate and follow the fields which come out of an information carrier and follows these evanescent fields and react to that and read out magnetically stored data. Okay, finally, this application, probably many of you have already the so-called mobile or cell phone included the GPS system. In future mobiles, one might have also electronic compasses which would assist the GPS system. So this is one of the upcoming applications also of GMR. I thank you for your attention.
グルンベルグ博士どうもありがとうございました。